This is Dr. Hubbard back with problems involving functions part 2. This is going to involve proofs, mainly with respect to injective, surjective, and bijective. So hopefully you enjoyed Dr. Lawson's proofs. Typically my proofs, I tend to prove things with more symbols and less words than him. If you read it out, it looks the same, but since I'm not actually with you, I'll try to use a few more words and a few less symbols. Symbols are handy for when you're writing something down because they go quicker, but if you're trying to communicate to somebody you're not with, you might use a few more words. So we've got a function from the integers to the integers defined by f of x equals 4x minus 1. We want to prove that it is injective but not surjective, okay? So to remember, to prove that something is injective, we are going to have to prove that it's injective for everything. To show that it's not surjective, we just have to show one exception, right? What does it mean to be injective? Well, remember, one definition of injective is that you take two things in the domain and you suppose, give yourself that they hit the same thing in the range, and then you say, well, were they the same thing to begin with? So a typical injective proof would pick two things in the domain, let x and x hat be in the integers. Since the domain and the codomain look the same, I'm going to just in parentheses say this is the domain. That's not required, but just keep in mind we're picking two things there such that, pick two things specifically so that f of x equals f of x hat. And then we want to ask, well, what happens? And if it's really injective, we give ourselves these things mapped to the same thing, and we'd like to get to something at the bottom that says, well, x equals x hat. I like to say, what do you have? That's what I have. What do I want? I'd like to say at the end, therefore, x equals x hat, and if this implies that, the end of my proof is going to be just, therefore, f is injective. So you can sort of even cheat a little bit and write the end of your proof first, but you have to write it in this order so that somebody reading it, you're trying to convince them, start with what you have, and now I have to convince them with this, how do I get to what I want? Well, what does this mean? Remember, they're reading top to bottom. F of x equals f of x hat. This means, well, that 4x minus 1, that's what f of x is 4x hat minus 1. So I guess that means 4x equals 4x hat. Now, if you were just reading along, so 4x hat equals 4x equals 4x hat, therefore x equals x hat. Oh yeah, I can see that. Divide by 4. You can even add a line. Divide by 4 if you want to, something like that. But you can see this is a proof that it's injective. How can I see that it's not surjective? Remember, surjectivity means, or being onto means that you hit every element of the codomain. However, we know 0 is in the codomain. I'll just emphasize, since there's a little bit of ambiguity, we've got the integers here and here. 0 is in the codomain, but can you see there's no integer that's going to map to it? But for no x in the integers, is it true that f of x, which equals 4x minus 1, equals 0? For that to be true. We need 4x equal to 1 or x equal to 1/4. And that's not an integer, right? So it is injective, it is not surjective. It is one-to-one, it is not onto. Unfortunately, some people use different terminology, so you're probably best served knowing both. Okay, now let's look at another problem. Let t be a function from polynomials of degree 2 to the integers, be defined by t of this polynomial equals b. And let's prove that it's not injective, but is surjective. Oh my, not injective. Okay, so what's that gonna look like? I have to come up with two things in the domain that map to the same thing. How could I get two things? I have to come up with a very specific example. What if I said, we know 2x squared plus 1x and 1x squared plus 1x, they're both degree 2 polynomials with integer coefficients, right? Let's see, t of 2x squared plus 1x, if you follow the definition, 2x squared plus 1x is 1, and t of 1x squared plus 1x equals 1. But 2x squared plus 1x is certainly not equal to 1x squared plus 1x. Therefore, it's not injective. But what about surjective? Now, to be surjective, I have to show that I hit everything here, right? So, let's think about that. Let's just pick an element here. Let k be an element of z. I need to come up with a way to hit that element. So then I need to come up with something that maps to it. Well, it turns out you could pick almost anything for a and c. So 1x squared plus kx plus 1 is an element of this, of the domain, and don't need to comma, let's see, and t of 1x squared plus kx plus 1 equals k. Therefore, t is surjective. Fair enough. Okay, one more, and this one is probably the most abstract of them. For sets A, B, and C, let F map A to B and G mapping B to C be functions. Prove that if G composed with F is surjective, then G is surjective. So let's let F be a function from A to B and G be a function from B to C. Be functions. That's something I have to work with. This is the domain of F. That's the codomain of F, domain of G, codomain of G. And let's assume G composed with F is surjective. Now, I want to show that G is surjective. This is what I have. This is what I want. Therefore, G is surjective. Okay? But what does this mean? I have that, I want that. What does this mean? And so often I'll even put this in parentheses. This is not necessary for your proof, but it's necessary for my thought process. This means for any C in the output, right? F takes in something in fact, maybe I should even make a chart here. G composed with F takes in things in A, they go through B, and they go to C. So for any C, that's just a thought over there. For any C in the codomain, being surjective means there exists A in the domain such that G of F of A equals C. We're almost certainly gonna have to use that fact at some point. That's what we have, okay? What do we want? We want G is surjective. What does that mean? To have G be surjective means we need to pick something in the codomain of G and find something in the domain of G that maps to it. So in order to prove this, that's what I want. I'm going to, for my proof, I'm going to let C be an element of the codomain of C. Now, I want to come up with a B here, but I can't do that. What I can do is the thing in parentheses. I can say, since G composed with F is surjective, choose A and A such that G of F of A equals C. So A lives here. I need something here, but there really is something here. Then F of A is an element of B, right? That's really what it is. F of A is an element of B. And here's the most important part, what do you know about F of A? Well, G of F of A is going to equal C. But that is the very definition of that. So I guess I didn't need to leave that much room. If G of that element equals C, G is surjective, and we're done.